We're going to look at an ND-YAG laser running, the mode is continuous wave. So let's get started with the inputs. It's a 1.064 micron or 1064 nanometer, depends on how you want to input this. I tend to work in nanometers on this. Although I say 1.06 microns, I mostly put 1064 nanometers. So I'm going to switch this to nanometers. Yeah, just something I want to do. Mode of operation, continuous wave. Its average power is 100 watts. The ANSI default for an unintentional or accidental exposure is 10 seconds. We have beam propagation parameters of the major axis and minor axis dimensions. Since it's circular Gaussian, the beam waist is 5 millimeters. Beam waist diameter is 5 millimeters, and the divergence is 2 milliradians. We have our observer range set at 0.5 meter. Here's our diameter at the observer range, just slightly over the diameter that is at the waist. We have an OD at the observer range of 4.7, and the worst case OD is 4.71. We'll take a look at that in just a moment. The NOHD is 1.1 kilometers. Let's see, for the CO2 running 2,000 watts and a lower beam divergence, that was 1.5 kilometers. And this is only running 100 watts, and we have 1.1 kilometers. So you can see that we kind of take a look at a YAG being a little more of a hazard than a CO2, and that is, of course, where we want to look at is the MPE. It's reflected in the MPE, where a CO2 is 0.1 or 0.1 watts per square centimeter or 100 milliwatts per square centimeter. This is 5.06 milliwatts per square centimeter, roughly about twice what it is for visible light. The skin MPE for this YAG for 10-second exposure is 1 watt per square centimeter. We have a times skin MPE of 634. So that tells us, is this a skin hazard? Yes, this is a severe skin hazard, and this is one of the worst lasers to get hit by, and that's because it penetrates deeper than any other wavelength. You can get about a 5 millimeter penetration from a YAG laser. Now, what helps is the fact that you're getting this penetration. You have a larger volume of tissue absorbing the energy. Okay, so that helps. But at 100 watts, this is going to be a really severe skin hazard. It's going to burn deep, and again, it's self-correcting. If you get caught by this beam, you won't do it again anytime soon. Okay, I will point out again, 1 over E squared circular Gaussian. Let's take a look here. So I guess this is just a little bit in the numbers and the rounding, because I wanted to look and see what the transmission, the transmission through the limiting aperture is about 98%. So that's the difference that we're seeing here, the worst case being 4.71 and the OD at observer range being 4.7, is this little bit of difference in how much power is really passing through the limiting aperture of 7 millimeters for the eye, 3.5 for the skin, so we won't get quite as much transmission through the limiting aperture for the skin. Let's take a look at how much power is passing through the limiting aperture, and yeah, if you're 97.7% and you're working at 100 watts, we would expect to see 97.7 watts transmitting through the limiting aperture. Okay. Whoops, that was watts. That's fooled me even. Okay, so now we're in percentage, and then that's watts, so we're back to percentage. All right. The diffuse reflection on this laser, we'll take a look at that. 100% spectral reflectivity. The viewing angle is 0. We'll keep a small beam on target because we are within the retinal hazard region. The source type can be point or extended depending on how far our observer is. And let's put our observer back to, say, a 1/4 meter here. And 600 second exposure duration. We have an NHC of about 0.8 meters. so it's a pretty significant NHC, diffuse reflection hazard. The OD at observer range should be about 1. Do we have a skin hazard from this, from the diffuse reflection? No, we don't. This is under 1, so there's no diffuse skin hazard from this particular laser. Let's take a look at our irradiance in the beam in case we want to talk about something like a barrier. We can see that it's almost 1,000 watts per square centimeter is what we would need to tell our vendor that we wanted to use. If it was a half a meter away, what happens if it's like 2 meters away? Well, it drops significantly. That's because we have a pretty high divergence here. The beam has gotten considerably larger. Let's go back and look at half a meter. This is because, again, we've got this 2 milliradian beam divergence. That's kind of large, so we will see a difference when we move from, well, I said 0.2. Let me put 0.5 in there. When we move from 0.5 to, say, 2 meters away, yeah, it makes a fairly significant difference in the diameter of the beam. So when we calculate the irradiance, we see that change in the irradiance here. So that's what we would relay to our vendor is if the barrier was going to be about 2 meters away, we'd need a barrier that could withstand at least 620 watts per square centimeter. All right. Let's see, what else do we want to look at? I think we understand how we get the average power irradiance in our beam, or how we get the irradiance of the laser. Power transmitted through the limiting aperture. Let me put this back to half a meter. Okay, power transmitted through the limiting aperture divided by the area of the limiting aperture. That gives us our irradiance of the laser. Divided by the MPE, take the common log, and that's where we get our OD value. So everything looks about right. Let me see if there's anything else we want to talk about. Look at C sub A here. C sub A for this wavelength, instead of being 1 like for the visible, the absorption at the retina is being corrected, and so we get a C sub A value of about 5 on this. Okay, so let's see, there doesn't seem to be anything else we need to look at, and so that's about it for this one.